Okay, I'm going to give another example of a group called the symmetric group. And this is basically where group theory started, I guess. If I consider a finite set, let's just say the set 1, 2, 3 up to n. I'm going to consider functions f. I'm going to call that set S. Functions which map S to S, but functions of a particular type. Oops. I'm going to consider bijective functions. So basically this is functions which have an inverse. So something like this. If I just consider S equals, let's just say 1, 2, 3. So the kind of functions I mean are, let's just say f of 1 equals 1, f of 2 equals 3, and f of 3 equals 2. So it's basically f has got to be 1 to 1 and on to. It's just a bijection. So in this case here, we can work out f to the minus 1. We just go backwards. Of 1 equals 1, because going backwards from 1 gives you 1. F to the minus 1 of 2 equals 3, because f of 3 equals 2. And f to the minus 1 of 3 equals 2. So there's a nice little example. And I'm going to consider the set of all functions from S to itself. So my group elements are functions from the set 1, 2, 3 up to n to itself with f invertible. So it's a bijection. So we had better check that this is a group. So the first thing to check, I guess, is it closed? Well, yes, it is, because if I've got to define the excuse me. I've got to define the group operation first. Well, that's just f composed with g is just fg, in the sense that f composed with g of an element x is f of g of x. This is quite tricky to understand. I'm going to spend a bit of time talking about this. So, what's going on here? This is the group operation which maps elements of my set to one another. So my set is functions from this set to itself. And there's a function f, and here's another function g. So I want to combine those two functions. It makes sense to do this, to get x, and then take g of x, and then take f of x. So I'm saying that f composed with g as a function of x, how do I do that? Well, I get x goes to g of x, which then goes to f of g of x. So this is my function here, which is this combined function f circle g of x. So this is telling you how to calculate it, but really what's going on is we've got a group operation which is do one function and then do the next. This is quite clearly closed, because if f and g are separately invertible, you can just invert it twice, basically. In fact, I'll write it down. fg to the minus 1 is g minus 1 f minus 1. It's just the same as you had in that free group example. So there it is. How do I know that that's the case? Well, fg, g times g minus 1 f minus 1 Well, it ought to be the identity. If I'm asserting that this is the inverse of fg, then multiplying these two guys together should be the identity. This is associative, so f, g, g minus 1, f minus 1, oops, equals f composed with f minus 1 is just the identity element. Actually, I'm getting somewhat ahead of myself here because I really ought to have started with the neutral element. But that's obvious, that's just f of x equals x for all x. So this identity here, if we define a function f with f of x equals x, then f is the identity. And of course you usually write it e, because e of x equals x. Okay, inverses, yeah, you've got an inverse, you just because it's inverse. It's invertible by design, because all the functions are invertible. And associativity, yeah, well, it's associative, isn't it? Okay, so there it is. Let's just give you some examples of that. I'll just start very, very slowly and just give a few examples of this. It's a very, very instructive group. I'm going to consider the set of three elements, 1, 2, 3, and I'm going to consider how I might map those. You'll see it written in different ways. 1, 2, 3, and then you write. Then you write where the number goes to. So 1, this is the identity, because 1 goes to 1, 2 goes to 2, and 3 goes to 3. There you go. How about this? 1, 2, 3, 1, 3, 2. 1 goes to 1, 2 goes to 3, and 3 goes to 2. That's just swapping 2 and 3 over. How about 1, 2, 3 goes to 2, 1, 3. That's just swapping 1 and 2 over. 1, 2, 3, 3, 1. No, what am I trying to do here? I'm trying to go 1, 2, 3. I'm trying to swap 1 and 3 over. 3, 1, 2. You see here I'm swapping 2 and 3. Here I'm swapping 1 and 2. And here I'm swapping 1 and 3. So these are all functions which are invertible. You can tell that they're invertible because they've got the domain and the range are the same set. So we can just invert these functions. How about 1, 2, 3 goes to 2, 3, 1? That's nice. 1 goes to 2, 2 goes to 3, and 3 goes to 1. 1, 2, 3 goes to 3. 1 goes to 3. 3 goes to 2, and 2 goes to 1. There we go. So they're sort of 3 cycles because we're sort of going round in a triangle, and these guys are just 2 cycles because we're just swapping 2 elements over. So, well, that's great, isn't it? We've got how many elements in here? Well, it's obvious that we've got 6 elements in here because that's equal to 3 factorial. And of course, if I was having a set of 5 elements, 1, 2, 3, 4, 5, I might be considering 1 goes to itself, 2 goes to 4, 3 goes to 2, 5, what's left? 3. There you go. I've got lots and lots and lots, and of course I've got 5 factorial elements here. The symmetric group, and I'll develop this idea as we go along. The symmetric group of order n is usually written S sub n, the symmetric group on n elements. And so we've made a little bit of a start here. There's a hell of a lot of detail, and it's quite a complicated and difficult subject to consider, but we've made a start on it. The crucial idea is that we're mapping a finite set to itself with invertible functions. And so once you've got that, you realise that you can just write it out like this, and of course the order of the group Sn is just equal to n factorial, because there are n factorial ways of writing the bottom line, basically. I'll just stop. I'm going to call that one alpha, and I'm going to call this one beta, and I'm going to work out what alpha beta is. Now, what was alpha again? 1, 2, 3, 2, 1, 3. 1, 2, 3, 2, 1, 3. composed with beta, which is 1, 2, 3, 3, 1, 2. So we defined alpha beta of x to be alpha of beta of x. So to work out what happens to these elements here, we've got to, this one's alpha and that one's beta, so we'll work out what happens to 1. So we unwrap it like this, so we get x, which is 1 in this case, because we want to figure out what happens to 1. Then we do beta of x, so 1 goes to 3, and then we do alpha of that. 1 goes to 3, 3 goes to itself. Right, where does 2 go? 2 goes to 1, 1 goes to 2, so 2 maps to itself, and 3 goes to 2, and 2 goes back to 1. So we can see it's nice and injective. I'm sorry, so it's still bijective, which is as it ought to be, and it's equal to that this function here, which sends 1 to 3, 2 to 2, and 3 to 1. Let's work out what beta alpha is, just for the hell of it. 1, 2, 3, 2, 1, 3, that's alpha, and beta was 1, 2, 3, 3, 1, 2. Let's do that. Again, what we're doing here is we're working out beta alpha as a function of x, where x is this set here, 1, 2, 3. So that's equal to beta of alpha of x. So we start 1, 2, 3, those are the elements of the set. 1 goes to 2, 2 goes to 1. 2 goes to 1 and 1 goes to 3, 3 goes to 3 and 3 goes back to 2 again. So they're not the same. They are not the same. So alpha beta is not equal to beta alpha, which is quite, well, I might say shocking, but it's quite a profound observation. That's not confusing. Well, of course they're not equal. You've just got to evaluate them. It's no more confusing or difficult than matrix multiplication being non-associative. But it's a nice finite group that's not that's not commutative. It's not abelian, and we'll see later that it's extremely non-abelian in a well-defined sense. So I'll come back to this group again and again and again. I'm going to define it in slightly different ways. I'm going to talk about it in different ways. We're going to look at subgroups of it. We're going to fool around with it. But for the moment, I'm just setting it out here. I use the set 1, 2, 3, but when you are fooling around with it, it is much better. It really is better to define it like this. You're going to think I'm nuts. Banana, grapefruit, apple. Okay? If you actually get these objects and actually permute them around, instead of fooling around with 1, 2, 3, if you've got an actual banana, one that you can pick up, there it is, there's a picture of a banana, and a grapefruit, and an apple, and you actually start permuting them around, not writing them down, but actually picking them up, you begin to appreciate the difficulty of, not the difficulty, but the subtlety of S3 as a group. Symmetric group on 3 elements. These 3 elements are very good ones. These, of course, professional way to do it, but it's much more fun to use actual fruit. Right, I'm going to stop there.